Module 7, Lecture B, Writing Text Files. By the end of this lecture, you will be able to open files in write and append modes to create or extend text files, write formatted strings and data to files from Python programs, and design simple scripts that read from one file and write processed output to another. File write modes. Write versus append modes. When working with text files, you must choose whether to open them in write mode or append mode. Write mode treats the file as new and replaces any existing content, like starting with a blank page. Append mode keeps the current data and adds new content to the end, like continuing in a notebook. This decision is important because it determines whether your program overwrites existing data or safely builds on it, which directly affects data safety and integrity. When saving results, like a daily lab report, write mode replaces the previous file, so you only keep the latest data, which is useful if you only care about the most recent outcome. In contrast, append mode adds new results to the end of the existing file, preserving a full history over time. This same choice between write and append modes applies to other records, such as customer support logs or sensor data, depending on whether you want a single current snapshot or a continuous cumulative record. When working with text files, choosing between write and append modes affects both data safety and organization. Write mode replaces the entire file, which can cause data loss if used carelessly, while append mode keeps existing content and simply adds new data to the end. Over time, though, append mode can create very large files that are harder to manage. Many developers, therefore, combine both approaches. For example, by appending to long-term logs while writing new summary files to keep better control over how their programs store and manage data. Python code. Write versus append modes. This section explains the difference between write and append modes when creating simple log entries. In write mode, the file is opened in a way that completely replaces any previous contents, so old log lines are lost. In append mode, the existing lines are preserved and new log entries are simply added to the end of the file. If your example requires it, you may first install any needed library using the appropriate package installation command. We begin by creating a variable that stores the name of the file we will work with. In this case, a file called experiment log. This gives us a single, clear reference to the file throughout the script. Using a variable for the file name makes it easy to change later if needed. It also improves the clarity and maintainability of the code, especially when performing multiple file operations. We open a file called experiment log in write mode, which clears any existing content so the file starts fresh. Within this context, we write a single line that records day 1 with a temperature of 72 degrees Fahrenheit, followed by a new line. This action initializes the log file so that at this point, it contains only this first experiment entry. We open the file named experimentlog.txt in write mode, which clears any existing content and prepares it for new data. Then we write a single new line that records the entry for day 2, stating that the temperature is 75 degrees Fahrenheit. As a result, any previous information in the file is removed, and it now contains only this new entry. we open the file called experiment log in read mode so we can view its contents without changing them. We then print a short message to indicate that we are about to show what is currently stored in the file. After that, we read and display the entire file content. This confirms that the earlier data was completely replaced by the most recent write operation, so only the latest entry remains in the file. We open the file named experiment log in append mode so that any new data is added to the end without changing what is already there. Within this context, we write a new line that records day 3 with a temperature of 70 degrees Fahrenheit. This new entry is simply attached after the previous ones. Using append mode in this way is useful for keeping a continuous log of data over time. After appending to the file, we open it again in read mode to verify the changes. Using the open function set to read, we enter a context block where we first print a message that we are checking the file after appending. We then read the entire contents of the file and print them out. This confirms that the original content is still there and that the new entry has been successfully added to the end of the file. This example shows how write and append modes behave when working with a text file in Python. First, the script creates a file and writes a line for day 1, but when it opens the same file again in write mode and adds a line for day 2, the original day 1 entry is erased. Reading the file now shows only the day 2 entry because write mode replaces all existing content. The script then opens the file in append mode to add a line for day 3. And reading it shows both the day 2 and day 3 entries. This demonstrates that append mode keeps existing data and adds new information at the end, which is essential for tasks like logging, where you need to preserve a history of entries. Replacing file contents. When you open a text file in write mode, all existing content is erased and replaced with whatever you write next, while the file's name and location stay the same. This means any previous data in the file is permanently lost. This behavior is useful when you want to completely regenerate things like reports or configuration files. However, you must be careful and only use write mode when you are sure you want to overwrite the file and accept the consequences. In many computing tasks, it is common to replace a file's contents so it always holds the latest information. For example, a script that updates a daily sales summary overwrites old totals and trends with new ones. And data analysis tools may overwrite intermediate results to keep only the current version. This approach prevents confusion from outdated data and ensures that anyone opening the file sees accurate, up-to-date content. Overall, overwriting files is a straightforward way to maintain clarity and correctness in file management. When replacing file contents, it is important to use habits that reduce the risk of accidental overwrites. A common practice is to write new data to a temporary file and only swap it in after you have verified the result. Some developers also keep timestamped or versioned backups so they can recover earlier versions if needed. Even for simple personal files like a to-do list, you should pause and confirm that you really want to overwrite instead of preserving existing data. Thinking this through each time leads to safer and more predictable file writing behavior. Python code, replacing file contents. This section explains how to safely replace the contents of a file using write mode. It shows that when you open a file in write mode and save new data, any previous text in that file is completely removed. By demonstrating how the old content disappears after overwriting, it helps beginners understand why they must use write mode carefully. The goal is to build awareness that write mode replaces rather than adds to existing file contents. This script uses only Python's built-in features, so you do not need to install any extra packages. Everything it requires already comes with Python. As a result, you can run it without using any installation commands. This keeps the script simple and accessible while it focuses on demonstrating file operations without relying on external tools. The code chooses a file name called example-report.txt to use for demonstration. This name identifies the text file that will be created or modified in the current working directory. By defining the file name once at the start, the rest of the script can consistently refer to the same file. This ensures that all reading and writing operations are performed on the correct file. We open a file called example report in write mode, which creates it if it does not exist or erases its current contents if it does. We set the encoding to UTF-8 so text characters are handled correctly. Within this file, we write the line daily report for Monday, followed by a new line. This shows that using write mode replaces any previous content with the new text we provide. After writing to the file, we open it again in read mode so we can see what it currently contains without changing anything. We specify UTF-8 as the text encoding to handle characters correctly. We then read all the file's contents into a variable called original text. This gives us a snapshot of the file's state that we can later compare to its contents after we make further changes. First, we print a label to show that we are about to display the original contents of the file before any changes are made, so the user knows what they are looking at. Then, we output the text that was read from the file. This lets us clearly see what the file contained before we overwrite it, making it easy to compare the original version with the updated one. We open the file called example report in write mode, which completely overwrites anything that was previously in it. Using UTF-8 encoding ensures the text characters are handled correctly. Within this context, we write the line that says daily report for Tuesday, followed by a new line. This shows that write mode clears the file first and then adds the new text as its entire content. After overwriting the file, we open it again in read mode to confirm the changes. We call the open function with the file name, set it to read, and specify UTF-8 encoding so special characters are handled correctly. Inside the context block, we use the read method to load the entire file into a variable. By examining this new content, we can verify that the old text has been fully replaced with the updated text. We print a label to show that the file contents have been overwritten so the user knows the original text is gone. After that, we display the new contents of the file, which now contain the updated text. This makes it clear that the earlier content about Monday has been fully replaced by the new content for Tuesday. This example shows that using write mode on a file completely replaces its contents. The script first creates or clears a file and writes a daily report for Monday, then reads and displays it to show the initial text. It then opens the same file again in write mode and writes a daily report for Tuesday, which erases the previous content. Reading the file a second time confirms that only the new text remains, illustrating how write mode overwrites everything that was there before. Creating new files. When you open a text file in write mode, the system will automatically create it if it does not already exist. This means your program can generate new files on the fly, as long as the folder is there and you have permission to write to it. The same idea applies when using append mode, which also creates the file if needed. This behavior is especially useful for tasks like logging data or creating reports, because the file is ready to receive information as soon as it is opened. When you open a file in write or append mode, the program can create it automatically, so you must decide carefully where and when new files should be made. In research, this might mean generating a separate file for each experiment using details like the date or parameters. And in business, it could mean creating a new file for each client invoice. The program does not need to check if the file already exists. It simply opens it for writing, and the system creates it if needed. This simplifies your code and makes it easy to scale from a few files to many, because the program can generate new files on demand. When using automatic file creation, you should plan how files will be organized, named, and handled when errors occur. Define a clear naming convention and directory structure, such as grouping files by project or time period, so your folders stay manageable instead of becoming cluttered. Make sure your program can respond properly if it tries to create a file in a directory that does not exist or where it lacks permission. For example, by notifying the user or choosing another location. By understanding how write and append modes behave and planning these details in advance, you can create files in a reliable and maintainable way. Python code. Creating new files. This section explains how to automatically create new text files using write and append modes. It shows that when you open a file that does not yet exist in a write mode, the system creates that file on the drive for you. It also emphasizes displaying the names of the files you create and their contents, so beginners can quickly confirm that the files were made correctly and contain the expected text. This comment explains that if extra libraries were ever needed, they could be installed with a package manager, but for this code, the standard Python library is enough. It emphasizes that the program is intentionally simple and does not depend on external packages. As a result, the code is easier to run, more accessible, and requires no additional setup beyond a basic Python installation. We begin by using the path class from Python's standard library module called pathlib. This module provides a simple, consistent way to work with file paths on different operating systems. By using path, we can create, modify, and access file paths in an intuitive and platform-independent way. This is especially helpful when writing programs that need to handle files reliably across multiple environments. We define a folder within the current working directory to store any new files we create. Using the path class from the pathlib library lets us handle file locations in a way that works across different operating systems. By choosing a folder name, like created logs, we keep all generated files organized in one place. This makes them easier to manage and find later. This code creates a folder called created logs in the current working directory using a path handling library that works across different operating systems. It is set up to automatically create any missing parent folders as needed, It also allows the folder to already exist without causing an error, so the program can continue running without interruption. We create a new file path by joining the base folder location with the specific file name temperature log Fahrenheit.txt. This gives us the full path where the new file will be saved. Doing this helps keep files organized and make sure the file is stored in the correct folder. It also helps prevent conflicts with other files that might have similar names in different locations. To create or overwrite a text file, you open it in write mode, which will automatically make a new file if it does not already exist. You specify the file location and use UTF-8 encoding so text characters are handled correctly. A context manager is used to manage the file, ensuring it is closed properly after you finish working with it. This protects against errors and prevents wasting system resources. The code records a temperature reading by writing a single line of text to a file. It states that the outside temperature is 72.5 degrees Fahrenheit at 3 in the afternoon. This information is formatted as a string and sent through a file writer that was opened in write mode. As a result, the temperature reading is logged into the newly created file. This example creates a path for a new file called Daily Notes Fahrenheit inside a folder named Created Logs by combining the folder location with the file name. It is used to show that when you open a file in append mode, the file will be created automatically if it does not already exist. This demonstrates how file paths and append mode work together to generate new files as needed. We open the second file in append mode so we can add new content to the end without changing what is already there. And if the file does not exist, it will be created. We provide the file location and use UTF-8 encoding to handle text characters correctly. The file is opened inside a context manager so that once the code inside the block finishes, the file is automatically and safely closed, which helps manage system resources properly. This example shows how using append mode to write to a file adds new text to the end without deleting what is already there. The code adds a line describing a comfortable evening room temperature of 70 degrees Fahrenheit. It illustrates that append mode is useful when you want to update a file with new information while preserving all existing content. We open the temperature log file in read mode and use UTF-8 encoding so the text is handled correctly. This lets us verify that the file was created successfully and allows us to read and inspect its contents. The code reads all the data from the temperature log file using a file reader, then trims any extra spaces at the beginning or end of the text. It stores this cleaned content in a variable for later use. This step ensures the temperature data is neatly formatted and ready for further processing or display. We open the file, whose path is stored in the append file path variable, in read mode, using UTF-8 encoding so we can access its contents, whether it was just created or previously appended to. Using a context manager, often introduced with the word with, ensures the file is automatically and safely closed after you finish reading. This proper closing is important for managing system resources and helping prevent file corruption. The program reads all the content from the Daily Notes file and then cleans it by removing any extra spaces at the beginning and end. This trimmed text is stored for later use, such as processing or displaying the notes. In this way, the data is prepared in a neat, consistent form before anything else is done with it. This line of code prints a message to the console that tells the user where the new temperature file has been saved. It builds the message using a formatted string, so the actual file location stored in a variable is inserted automatically. This gives the user immediate feedback about the exact save location of the file. The code prints out the contents of the temperature log file to check what was saved. It uses a formatted message that includes the data previously read from the file. This makes it easy to see exactly what the file holds and confirm that it was created correctly. In short, the printout serves as a quick verification that the file contains the expected temperature information. The code prints a message to the console showing the path of the notes file that was created or updated. This gives the user immediate confirmation that the file exists and where it is stored. It also helps with checking that the program worked as expected. In addition, it can be useful for debugging if something goes wrong with file handling. The code displays the contents of the daily notes file, so you can confirm what has been added or written to it. By printing the file's current text, it lets you quickly verify the results of earlier file operations. A formatted message is used to present this content clearly, making it easier to review and check for correctness. This script shows how to create and work with files using Python's standard library. It first makes sure a folder for logs exists, creating it if needed. It then opens a temperature log file in write mode, which creates the file if it does not already exist, and writes an outside temperature reading. Next, it opens a daily notes file in append mode, which also creates the file if missing, and adds a note about room temperature. Finally, it reads both files and prints their locations and contents to confirm that write and append modes correctly handle file creation and content storage. Writing formatted text. Writing with write. To create or update a text file in your program, you use the file object's write operation, which copies a string into the file at the current cursor position. This operation only accepts strings, so you must first convert any numbers, dates, or other data types, such as calculated grades or sales totals, into string form. After conversion, the string is written into the file and becomes part of its stored contents until you later change or remove it. When using a write operation, you first need to build one complete text string that contains all the information you want to store. This usually means combining pieces like timestamps, usernames, and actions into a single, well-structured line. You can separate these pieces with spaces, commas, or other simple separators. After you assemble this full string, you pass it to the write operation, which saves it exactly as you created it, without adding any extra formatting on its own. When you write data to a file, the program has complete control over the exact text that is stored, which means any formatting mistakes in your strings will appear exactly as written. If you forget a space between a first and last name, they will run together. And if you want labels like the word total before a number, you must include them yourself. This precise control is useful because it lets you tailor the file for different purposes, such as comma-separated values for analysts or specialized layouts for researchers. Since the write operation records exactly what you provide, it is a key step in turning data into well-structured text on disk. Python code, writing with write. This topic shows how to write text data into a file using a basic write operation. It explains that numbers must first be converted into their string form before they can be written. After writing, you then open and read the file to display its contents. This final step confirms that the data, including spacing and formatting, has been stored correctly. This comment explains that the script only uses Python's built-in modules, so you do not need to install any extra libraries. It serves as a reminder that everything required to run the script already comes with Python. This helps users feel confident that the script will work without additional setup. In short, the script depends only on what is included in a standard Python installation. We define a variable to store the current temperature in degrees Fahrenheit, using the value 72.5 as a typical measurement. Keeping this temperature in a variable allows the script to work with it more easily. For example, we can later convert it to another unit, prepare it for display, or record it in a log. We create a readable message for the user by taking the numeric current temperature in Fahrenheit, converting it to text, and then combining it with a short descriptive phrase. We attach the words that label it as the current temperature and add the Fahrenheit unit. The result is a clear, complete sentence that states the temperature in a human-friendly way. We define a variable to store the current humidity as a percentage, using the value 48 as a typical example. This numeric value will later be turned into a descriptive text that explains the humidity level. That formatted text will then be written to a file so the environmental data is logged in a clear, human-readable way. This line builds a message that records the current humidity. It starts with the phrase current humidity, followed by a colon and a space, then converts the numeric humidity value into text so it can be joined with the rest of the message. Finally, it adds the word percent to complete a readable sentence that can be written to a file or shown on a display. We create a new text file called weatherlog.txt by opening it in write mode, which either makes the file if it does not exist, or clears it if it already does. We use a with statement as a context manager so that Python automatically handles opening and closing the file. This guarantees the file is properly closed after the code inside the block runs, even if an error happens. Inside this block, we work with the file through a file object that lets us write data into the weather log. The program writes a temperature message into a text file by calling the file's write method with a string that includes the current temperature. It also adds a newline character at the end of this string. This makes sure that any later data written to the file starts on a new line, keeping the file's contents neatly separated and easy to read. The code logs humidity data by writing a humidity message into a text file. It uses the file's write operation to add the message and then a new line character. This makes sure each humidity entry appears on its own line. As a result, the weather data is neatly organized and easy to read when the file is opened later. We open the text file named weatherlog in read mode so we can look at its contents without changing anything. Using a with statement to do this is important because it automatically closes the file when we are finished. This helps prevent wasting system resources and reduces the risk of file corruption. Overall, this approach is a safe and reliable way to read data from a file. The program reads the entire file at once and stores its contents in a single string in memory. This approach makes it easier to access and work with the file's data. By having all the text in one place, later operations or checks on the file become simpler to perform. We begin by printing a short label that describes the contents of the file we are about to show. This label tells the listener what the upcoming output represents and provides context for the data. Including this simple description makes the results easier to follow and helps keep the overall output organized and readable. The code prints the contents of the file that were previously read and stored, allowing you to verify that the data was written correctly. By viewing the output, you can check that the text, formatting, and spacing match what you intended. This confirmation step helps ensure that the file write operations were successful. This script shows how to write formatted text to a file and then verify what was written. It creates messages that describe a temperature in Fahrenheit and a humidity percentage, then opens a text file in write mode and saves each message on its own line. After closing the file, it opens the same file in read mode, reads all the text back into a single string, and prints it. This confirms that the data was written correctly and that the formatting of the stored messages is as intended. Inserting line breaks. When writing text to a file, you must explicitly insert line break characters to mark where one line ends and the next begins. These special characters create the familiar line-by-line structure you see in text editors. Without them, the file would be a single continuous stream of characters that is difficult to read and process. Whether you are logging data or saving simulation steps, adding line breaks in the right places is essential for producing clear, well-structured files. When writing text to a file, you create new lines by inserting a new line character wherever a new line should begin. This marks where one line ends and the next one starts. For example, each student name or each daily sales total should be followed by a line break, so they appear on separate lines. Placing line breaks at logical points creates clear structured records that are easier for both people and programs to read and analyze. Line breaks are useful for organizing complex text files, not just for simple lists. You can group related lines into sections and use double line breaks to separate those sections clearly. In reports, a heading followed by lines of detail with breaks can mirror a document structure, and in logs, each line might hold a timestamp and message, with breaks marking different events. Used carefully, line breaks turn raw text into a clear, easy-to-navigate document for both people and computer programs. Python code, inserting line breaks. This script demonstrates how newline characters control line breaks when writing to files. It writes the same data twice, once using explicit newline characters and once without them. It then reads both files and prints their contents so you can clearly compare how the presence or absence of newline characters changes the way the text appears. This comment explains that you do not need to run any pip install commands for this example. The code is meant to be simple and self-contained, so it works without adding extra packages. This makes the script easier to use, especially for beginners who may not know how to manage Python packages. As a result, they can run the code right away without any additional setup. We begin with a list of 3 student names: Alice, Bob, and Charlie. This list serves as simple data we can work with while exploring how line breaks change the way information is written to and read from files. Using a list makes it easy to loop through the names and perform different file operations on them in later steps. We open a file called names no breaks in write mode to store student names without line breaks. Using a with statement makes sure the file is automatically closed when we are done. Inside this block, we join the list of student names into one long string with no separators. We then use the write method to save this string to the file, so all the names appear consecutively with no spaces or new lines. We create or overwrite a file called names with breaks to store student names, and we open it in a mode that allows writing. Then we go through each name in the list of students and write it into the file. After each name, we add a new line character so that every student appears on its own line. This way, the file clearly separates each entry and is easy to read or process later. We open the text file in read mode so we can access the data that was previously saved without line breaks. Using a context manager automatically closes the file afterward, which helps avoid wasting system resources. We then read all of the file's contents into a single variable, which now holds the raw data, ready for display or further processing. We open the file that stores the names with line breaks in read mode and assign it to a file object. Within this context, we read the entire contents of the file using its read method and store the result in a variable. This gives us direct access to the full raw text of the file, including all the new line characters that were previously written. With this content loaded, we can then process or inspect the names exactly as they appear in the file. We first print a label to indicate that the next output shows content without explicit line breaks, so it is easy to recognize visually. Then we display the file contents that were read earlier, where the student names are written continuously with no new line characters. This illustrates how the data looks when line breaks are not used and all names appear in one long sequence. We first print a label to indicate that the upcoming output will contain explicit line breaks, so it is easy to distinguish from output without them. Then, we display the content read from the file that stores names separated by new line characters. As a result, each name appears on its own line, clearly demonstrating how new line characters control line breaks in the displayed text. This script shows how new line characters change the way text appears in a file. It writes the same list of student names to 2 different files, but formats them differently. In the first file, all the names are written in one continuous line with no breaks. In the second file, a new line is added after each name. When you read and print these files, the first one shows all the names joined together, while the second one displays each name on its own line, demonstrating the effect of new line characters on text formatting. Formatting output lines. Instead of just dumping raw data into a text file, you should think about how each line is structured and presented. Formatting means arranging, spacing, and labeling information so it is easy for people to read and for programs to process. For example, a daily sales report might always list the date, then the product name, quantity, and total price in the same order. This consistency turns each line into a clear template filled with data, rather than a random string of characters. Think of each line in your file as a sentence whose structure you control. You choose the order of information, the punctuation, and how much detail to include. For example, you might start with a timestamp, then an event label, then a message, or separate financial values with commas or tabs for easy import. You are not just recording values, but designing the format, including decimal places, units, and rules for missing data. The goal is a clean, consistent, column-like layout that is easy to read in a text editor. As you gain experience, you will find that well-structured output lines make later work much easier for you, your team, and automated tools. A consistently formatted file supports quick analysis, like reviewing grades or sensor readings, because each line follows a predictable pattern. This predictability also simplifies writing programs that read the file, since important pieces of information, such as a user ID at the start of a line, can be extracted without guesswork. By planning for the needs of the file's end users and keeping the format consistent, you turn your output into a reliable record that supports analysis, debugging, and long-term storage. Python code. Formatting output lines. This lesson shows how to write neatly formatted report lines into a simple text file, using formatted strings to create aligned columns for clear, readable output. You will practice generating these aligned lines, saving them to a file, and then reading the file back into your environment. Finally, you will display the formatted lines again to confirm that the structure and alignment are preserved. This line serves as a reminder to install any external Python package that the script depends on before running it. If the script uses a library that is not part of the standard Python installation, you must make sure that library is installed. This is usually done with the pip package manager, which downloads and installs Python packages from the Python package index. Ensuring these dependencies are installed helps the script run correctly without errors. We define a list called sales data that stores individual sales as tuples, where each tuple holds the date, the item sold, the quantity, and the total revenue. This structure keeps all key details of each sale together in one place. By organizing the data this way, we can easily access and manage sales information. It also makes it straightforward to generate reports or perform further analysis on the sales records. We create a new text file called Daily Sales Report, opened in write mode with UTF-8 encoding, so any existing content is replaced and special characters are handled correctly. In this file, we build a header line that labels the columns as date, item, quantity, and total dollar amount. The date and item labels are left aligned within fixed widths, while quantity and total dollar are right aligned within their own fixed spaces. This formatting keeps the columns neatly lined up when the file is viewed. Finally, we write this formatted header line to the file and move to the next line. The code creates a separator line by repeating a dash character to match the length of the header line. This makes the separator exactly as wide as the header, keeping everything neatly aligned. The separator is then written to the file to provide a clear visual break between the header and the data rows. This improves the readability of the output. The program processes each sale by unpacking the date, item, quantity, and total from the sales data. It then builds a neatly aligned text line using formatted strings. The date and item name are left aligned in fixed width spaces, while the quantity and total are right aligned so the numbers line up. The total is shown with 2 decimal places to keep currency formatting consistent. Each formatted line is written to the report file on its own line to keep the report easy to read. The program opens a file called Daily Sales Report in read-only mode, so it can access the text without changing it. It uses UTF-8 encoding to correctly handle all characters in the file. After opening the file, it reads all of the text into a single variable. This variable now contains the full contents of the file, ready to be processed or displayed. The code first prints a short message to let the user know that the formatted daily sales report will be shown next, setting the context for the output. It then prints the contents of the report file, which were previously read into memory. This displays the structured report directly in the notebook, so the user can review the formatted data without opening the file separately. This script generates a neatly formatted sales report and saves it to a text file. It starts with a list of sales records that include the date, item name, quantity, and total price. The script opens a new file, writes a header with aligned column titles, adds a separator line, and then writes each sales entry so it lines up under the correct column. After closing the file, it reopens it in read mode and prints the finished report to the console. Overall, it demonstrates how to use formatted strings in Python to create a clear, aligned text report. File transform scripts. Read, process, write flow. When writing a script that reads from one file and writes to another, think of it as a simple cycle of reading, processing, and writing. Open the input file that holds the raw data and an output file for the clean data. Then handle the file line by line so you do not load everything into memory at once. Applying any needed changes, such as trimming spaces or adjusting text case. After processing each line, immediately write the result to the output file. Continue this pattern until all lines are handled, then close both files to keep the script organized and each step clearly defined. The read, process, write flow is a flexible pattern that works for both small and large tasks without changing your script's basic design. Your script reads each piece of data, processes it to extract or standardize key information, and then writes out a simpler, cleaned version. This can apply to web server logs, where you keep only important details like date and time, or to survey data, where you split and normalize responses. Using this approach keeps your script modular, which makes it easier to test, debug, and adapt to new data sources. Organizing your script into a clear sequence of reading, processing, and writing makes tasks easier to manage and adapt. First, you safely read data from the input file. Next, you process it by applying transformations such as anonymizing or reformatting, which can be tested on their own. Finally, you write out the processed data in a consistent form, whether as plain text or a structured report. Keeping these steps separate supports a disciplined approach that can be reused for different goals, like summarizing transactions or cleaning survey data. Python code. Read, process, write, flow. This activity demonstrates a simple read, process, and write flow using small text files. You will read lines from an input file, apply a transformation to each line, and then save the processed lines into a new output file. Finally, you will display the results so you can see how the original text has been changed by the processing step. This example is designed to be beginner-friendly because it does not require any external libraries. It uses only Python's built-in features, which keeps the code simple and easy to follow. By avoiding extra dependencies, the example lets you focus on the basic flow of reading data, processing it, and writing the result. This helps learners understand the core steps without being distracted by additional tools or setup. We begin by creating a sample input file called visits raw, which will hold several lines of raw text data. We open this file in write mode so we can create it or replace anything already inside. In the file, we store 2 visit records, each with a date, a web page name, and extra spaces. One line records a visit to home.html on January 1st, 2024, and the other records a visit to about.html on the same date. The extra spaces are intentional because this file is meant to simulate messy, unprocessed data that we will later clean and analyze. The processed line function takes a single line of raw text and cleans it up to keep only the important parts. It first trims any extra spaces at the beginning or end, then splits the line into separate elements based on spaces. From these elements, it keeps only the first 2, which are considered the key pieces of information. It then joins these 2 elements back into one string with a space between them, and returns this simplified, cleaned line. We begin by choosing a name for the output file that will store the processed data, then open the input file for reading and the output file for writing at the same time so both are managed safely. We loop through each line of the input file, sending it to a processing function that cleans and formats the text as needed. After processing, we write the updated line to the output file and add a newline character to keep the structure correct. This cycle repeats until every line from the input file has been processed and saved to the output file. We now display the processed visit records from the cleaned output file. To do this, we open the cleaned file in read mode and go through it line by line. For each line, we remove any extra spaces at the beginning or end and print it to the console. This lets us quickly verify that the visit data was processed and saved correctly. This script shows a simple read, process, and write workflow using text files. It first creates an input file with lines that include dates, page names, and extra spaces. The program then reads each line, removes the unnecessary spaces, and keeps only the date and page name. These cleaned lines are written to a new output file, which is then read back and printed. The result is a clear demonstration of basic text file handling and straightforward data cleaning. Line filtering basics. When transforming text files with a script, a common technique is line filtering. The script reads each line, checks whether it meets a specific condition, and writes only the matching lines to a new file. For example, it might keep lines that contain a certain word or start with a particular prefix and skip all others. This approach is useful for extracting error messages or isolating specific pieces of data from larger reports. When filtering lines in a text file, you first need clear rules that describe which patterns you want to keep or remove. These rules can be simple, such as keeping only lines with a certain keyword or dropping blank lines, or more complex, such as checking whether a field is above a threshold or a date falls within a specific range. For example, you might keep only high-priority customer support tickets by looking for a priority marker in each line. With sensor data logs, you might discard lines that are missing fields or contain non-numeric characters. In all cases, the key idea is to define a decision rule that determines whether each line is kept or ignored. When designing line filtering scripts, focus on deciding which lines to keep while preserving the overall file structure. Make sure to handle edge cases, such as keeping headers, trimming extra spaces, and normalizing text before applying your filters. In practical tasks like cleaning invalid emails from a mailing list or keeping only lines that mention certain systems, clear filtering rules are essential. By defining these rules carefully and addressing these details, you can turn long, cluttered input files into concise outputs that are ready for analysis. Python code, line filtering basics. This lesson shows how to perform simple line filtering when copying text from one file to another. You will see how conditions are used to decide which lines are kept and which are discarded. The goal is to compare the original lines with the filtered result so beginners can clearly understand how the filtering process changes the output. This note explains that the script needs no extra installation steps because it relies only on Python's built-in libraries. In other words, the code is self-contained and does not depend on any third-party packages. As a result, it is easy to run in any standard Python environment without additional setup. We first choose a name for the input file, which will store the original support ticket data. Then we choose a name for the output file, which will store only the tickets that are marked as high priority after filtering. Using clear, descriptive file names makes it easier to understand the role of each file in the script and how the data flows from the full set of tickets to the filtered high priority tickets. We begin with a small list of example support tickets, where each ticket is a text line containing an ID, a priority level, and a brief issue description. One ticket is low priority and describes a printer problem. Another is high priority about server room temperature. A third is medium priority about delayed email delivery. And a fourth is high priority about a frozen cash register screen. This collection of varied priority levels and issues is used to demonstrate how to filter tickets based on their priority. We start by opening the input file in write mode so we can create it or replace any existing content. Using a context manager ensures the file is automatically closed when we are done. We give the file a name and set the encoding to UTF-8 so it can store special characters correctly. Inside this block, we loop through each entry in the list of example lines and write it to the file, adding a new line after each one so they appear on separate lines. This process prepares the input file with sample data that will later be filtered based on priority. We begin by opening one file to read from and another to write to, so we can examine each line and decide whether to keep it. As we read each line from the input file, we clean it by removing newline characters and extra spaces. We then check whether this cleaned line contains the phrase priority high. Only lines that meet this condition are written to the output file, and each accepted line is followed by a new line so the output remains properly formatted. We begin by printing a message to indicate that we are about to show the original contents of the tickets file. Then we open the file in read mode using UTF-8 encoding, so any special characters are handled correctly. We loop through each line in the file, remove extra white space and newline characters, and print the cleaned line to the console. This lets us view all the original support ticket entries in a neat, readable form. We begin by printing a short header to show that the program is about to display the filtered high-priority tickets. Then we open the output file, which contains only these tickets, using UTF-8 encoding, so special characters are handled correctly. As we read each line, we remove extra spaces and newline characters to keep the output clean. Finally, we print each cleaned line so that only the high-priority tickets are shown. This script shows how to filter lines in a file using simple conditions on support ticket data. It first writes several example tickets with different priority levels to an input file. Then it reads all the tickets, selects only those marked as high priority, and writes those to an output file. When run, it prints all the original tickets, followed by only the high-priority ones, demonstrating how conditional filtering can be used to selectively process and store data. Writing summary files. Beyond basic file operations, creating summary files is a powerful way to extract key information from large datasets. These summaries capture essentials like totals, averages, and counts so people and programs can quickly understand the data. For example, instead of reading every transaction in an online store log, a summary might report total sales, revenue, failed payments, and top products. The detailed file still holds all the raw information, while the summary provides a concise report for managers or dashboards, helping decision-makers focus on what truly matters. To create a useful summary file, first decide what key questions it should answer. Then read through the original data line by line, pulling out only the information you need. As you go, update any counts or structures in memory so you can compute important results. When all the data has been processed, write a new file that contains just these essential outcomes in a clear, reusable format. For instance, when analyzing student quiz scores, you might record how many students there are, the highest and lowest scores, the average score, and how many students scored above a chosen cutoff. This summary file turns raw data into a concise story that emphasizes the most important insights. Summary files help different systems and teams process information and work together more effectively. For example, a research group might compress large sensor datasets into daily summaries that show key statistics and unusual events, while a customer support team might summarize chat logs with counts, common issues, and average resolution times. These concise summaries can then be shared with stakeholders or fed into reporting tools to reveal patterns and trends. By focusing on the most relevant data and presenting it clearly, summary files become practical tools for analysis and decision-making. Python code. Writing summary files. In this lesson, you will learn how to read a raw data file and generate a concise summary report. You will see simple processing steps that count how many records are in the file and calculate basic numeric statistics. The goal is to help beginners understand how to turn detailed log data into a clear, readable summary. Standard libraries are available, and you can install any extra library only if it is truly needed. We begin by choosing names for two files used in our script. The input file, called daily sales log, holds the raw sales data we want to process. The output file, called daily sales summary, will store the report we generate from that data. Defining these file names at the start makes it easier to handle all file operations consistently throughout the program. We begin by creating or overwriting a file called dailySalesLog.txt in write mode using UTF-8 encoding so text is stored correctly. In this file, we first write a header line that defines 3 columns: time, customer, and amount in dollars, which sets the structure for our sales data. Then we add 2 sample sales entries. One records a sale at 9:15 by Alice for $23.50, and the other records a sale at 10:02 by Bob for $15. These initial records give us basic data that can be processed later in the script. We open the existing sales file in append mode so we can add new data without changing what is already stored. Then we write several new sales records, each with a timestamp, a customer name, and a dollar amount. This process expands the dataset and provides additional information that can be used for later processing and analysis. We begin by creating 2 variables to track sales data. One variable counts how many sales records we process, starting at 0. The other stores the total revenue in dollars as a decimal value, also starting at 0. Setting these initial values is essential so we can correctly accumulate sales and calculate statistics later in the script. We begin by keeping track of the smallest and largest sales amounts using 2 variables that start out with no value, meaning no sales have been processed yet. As each sale comes in, we compare it to the current smallest and largest values and update them when needed. By the end, these variables hold the minimum and maximum sales amounts, which are essential for calculating accurate statistics for the summary report. We begin by opening the input file in read mode with UTF-8 encoding so it can correctly handle special characters. The first line, which is the header, is read and stored but not processed further. After that, we loop through each remaining line in the file, treating each one as a separate sales record. Within this loop, we can extract and analyze the data from each record as needed. The code processes each line of sales data by trimming extra spaces and splitting the line at commas to separate the fields. This produces a list of text values that represent parts of a sales record. From this list, the first value is stored as the time, the second as the customer's name, and the third as the sale amount. The code first converts the text version of the amount into a floating point number so it can be used in calculations like totals or averages. This step turns the sale amount into a usable numeric value in dollars. After that, it increases the sale counter by 1 to record that another sale has been processed. The code adds each new sale amount to the total revenue, keeping a running sum. It then checks whether the smallest sale has been set yet or whether the current sale is lower than the smallest one recorded so far. If either is true, it updates the smallest sale to the current amount. This way, the smallest sale value always represents the lowest sale seen up to that point. We compare each sale amount to the current largest sale and update the largest value when needed. If no largest sale has been set yet, or if the current sale is bigger than the one stored, we replace the stored value with the current amount. By repeating this check for every sale, we ensure that the final stored value is the highest sale amount in the entire set. To find the average sale amount, we first check whether there is at least one sale, so we do not divide by 0. If there are sales, we calculate the average by dividing the total revenue by the number of sales. If no sales were recorded, we simply set the average sale amount to 0. This approach safely handles empty input data and keeps the program from crashing. We start by opening an output file for writing, which will hold our summary report. The file name is determined by the chosen output file name. In this file, we first write a header line stating that it is a daily sales summary report. Then we record the total number of sales, using the stored sale count to give a quick overview of how many transactions took place. The code writes 3 key sales metrics to the summary file, each formatted to 2 decimal places. It records the total revenue in dollars, then the average sale amount to show a typical transaction size. Finally, it saves the smallest sale amount to highlight the lower end of sales transactions. The code adds a line to the summary file that reports the largest sale amount in dollars. It uses formatted text to insert this maximum sale value and shows it with 2 decimal places for clarity. This creates a quick, readable reference to the highest transaction in the sales data. The program opens the summary file in read mode so it can access its contents without changing them. It then reads everything from the file into a single text variable stored in memory. After that, it prints this text while trimming any extra spaces at the beginning or end. This final step helps confirm that the summary file was created correctly and contains the expected output. This script works with a sales log file to create a simple summary report. It first generates a text file containing sample sales data with timestamps, customer names, and sales amounts. Then reads the file to count how many sales occurred and calculate the total revenue. As it processes each entry, it also tracks the smallest and largest sale amounts. Afterward, it computes the average sale and writes all results to a summary file, including the number of sales, total revenue, average sale, and the minimum and maximum sales. Finally, it prints this summary, demonstrating basic file handling and data aggregation in Python to turn raw sales data into a concise report. In this lecture, you learned to open files in write and append modes to create or extend text files. Write formatted strings and data to files from Python programs. And design simple scripts that read from one file and write processed output to another. In the next module, Module 8, we will go over errors and debugging. Thank you for your attention. See you all in the next lecture.